Thank you. Hello, everyone. A very good evening. And first of all, thank you for joining us this evening for what I think is one of the most fundamental quests of humankind, of our species. And we are going to take a tour of the very cutting edge of that quest. So first off, I would like to just thank a lot of people who have made it possible where we are today, this search for life. Here I'm listing many of my collaborators, several of whom are in the audience today as well, but also just this field of exoplanetary science that has just flourished over the last 30 years. It was only 30 years ago, we didn't know of any planet outside the solar system. And here we are talking about the search for life already, right? So if you think about it, that's huge. And I'll go a little bit more into the philosophy very quickly. But first, I would just like to start with a lot of gratitude for those thousands of people who have made this happen over the decades. And it's a tribute to all of them and to us as a species that we are here talking about this. So with that, I always like to start with this philosophical note, just to set the stage here, just so we realize how the magnitude of the situation here. For thousands of years, we as a species on this planet have always wondered, are we alone in this universe? Well, we didn't know much about the universe until just about 100 years ago. Okay? So it was, if you think about it, it's only 500 years ago that the Copernican revolution took shape. That is us realizing that we are actually not at the center of the universe, not even at the center of our solar system. It's just the sun that's at the center of solar system, and we are going around it. And even that got a lot of people into a lot of trouble. Just imagine that, right? And that was not that long ago. That's just 500 years ago. Okay? And did you know that just 100 years ago, we didn't know what the sun was made of? Isn't that crazy? Just 100 years ago. And all the physics that we know today, the quantum mechanics and everything, that came just about 100 years ago. Okay? So this year actually is very special because this is the 100th anniversary of the year when Cecilia Payne, also a Cambridge graduate, first established that the sun is actually made of hydrogen. And that was only 100 years ago. Okay, so we didn't know how the stars shine. And only 30 years ago, as I already mentioned, we didn't know if there was any planet outside the solar system. So for all we knew, it's just the solar system and that's it, as far as planets and definitely life is concerned. And in these 30 years, now we know of thousands of exoplanets, and we are beginning that ultimate quest on asking, is there life on any of those planets? Okay? So I wanted to for all of us to take a moment to realize how far we have come as a species to be even able to sit here and have this discussion. Right? To have any realistic chance of even answering that question is huge. Okay? So with that, I'll start my talk. So now you have the coordinates set up. So this is a very, very profound moment, and I feel hugely privileged to be here and sharing with you some of those insights happening at the very cutting edge. So in this talk, you'll see a lot of introduction to techniques that we use. You'll see some novel theoretical developments. You'll see some cutting edge observations. And by the end of it, I hope to convince you that it's looking good. Whatever good means, right? So we want to detect, ultimately, right, if we are talking about life on another planet, the holy grail is to be able to detect life on an Earth-like planet around a sun-like star. Okay? Life on an Earth twin. The basic common sense question, there are two questions to ask. What are the requirements in terms of, do we know of such a planet elsewhere before we go about finding life? And do we have the observational capability to detect life on such a planet, even if we knew one? Right? The answer to both of those questions is no. Okay, started. Sorry for the disappointment, but I promised you good news. So stay tuned. Where do we go from here? So we started off by saying, we don't have an Earth twin yet, and we don't even have the capability to detect life on such an Earth twin. And there are enormous efforts happening around the field of exoplanetary science in making both these answers to be yeses. But that's a few decades worth of effort to answer both of those questions as yes. So coincidentally, just completely out of the blue, in the last 2 decades, and I don't think most people would have predicted that when we first detected exoplanets. But what we have learned is that, so today we know about over 6,000 exoplanets out there. And what we have learned is that planets between Earth and Neptune in size dominate the exoplanet population. Right? There are no such planets in the solar system. So there are the terrestrial planets, Earth and smaller. There are the giant planets, Neptune, Uranus, and larger, but nothing in between. But in the exoplanet population, those are the planets that dominate the exoplanet population. These are called sub-Neptunes. Okay? So we don't know what these planets are like, what their atmospheres could be, what their interiors could be like. And lots of planet detection surveys are focused on detecting such planets around nearby stars, because these sorts of planets open a wide range of fundamental questions that we might be able to answer. Pertinent to the talk today is that a new angle is opening up in the search for life, in terms of trying to understand if some of these sub-Neptunes could actually be habitable, even if they're not Earth-size. Okay? So here I'm showing you just a cartoon. On one end is the Earth and terrestrial planets. On the other end is Neptune. And in between, there is this vast diversity of planets that are possible. So the big question to ask is, can any of these planets be habitable? And that's what we are going to focus on in today's talk. So once we have a few targets, I'm giving you a brief 101 lecture here on some techniques. Once you have identified a planet that is potentially habitable, what do you do? How do you go about trying to find life? So even before getting to the life question, the big picture is that we, over the last couple of decades, have been trying to understand atmospheres of planets using various techniques. And ultimately, those atmospheric signatures might hold the clues to life on the surfaces of some of these planets. Okay? So this is just an example, a cartoon showing that in different wavelengths, if you're looking at a UV versus infrared or optical, you probe different lengths, different depths in the atmosphere of a planet with various instruments in these wavelength ranges. And as you do that, you can also observe a wide range of physical and chemical processes in these atmospheres. So you can see their processes. If you're looking in the UV, you look at atmospheric escape process at the very top of the atmosphere. But if you look at the infrared, you can probe deep into the atmospheres and try to understand, infer some of the physical process like atmospheric dynamics and also chemical compositions of the atmospheres close to surface. Right? So if you are looking at ultimately habitable planets and wanting to understand something, is there life on the surface, what you're trying to say is the chemicals released by life on the surface coming into the atmosphere. And if you look at spectroscopy of these planets, you might be able to detect some chemicals. So that's where we're going. So one technique that allows us to do this is called the transit technique. I'll just show you a cartoon here. You may have heard of transiting planets. This is basically where the orbital plane of the planet is inclined in such a way that the planet passes in front of the star as viewed by the observer, which is you at this point. Right? So when the planet goes in front of the star, you'll see that if you follow the starlight, you'll see a dip in starlight when the planet is passing in front. And that dip is basically proportional to the ratio of the areas of the planetary disk over the stellar disk, basically a radius of the planet or radius of star squared. Okay? So that gives you a measure of the size of the planet if you know the stellar radius. You can take one step further. So I'll show you a cartoon here. So that's basically it. So the size of that dip is basically that delta transit, which is called as the transit depth. On top of it, you also have an atmosphere of the planet, which is transparent in some wavelengths and not in others. So if the molecules in that atmosphere absorb at some wavelengths, light at those wavelengths is going to be absorbed more. So you see more absorption as a function of at those wavelengths. So that is what is shown here in this red curve here. This is the theoretical curve, the red one, and the blue points are the data obtained with the Hubble Space Telescope for a giant planet, for a giant Jupiter-sized planet around a sun-like star. But that is an example of what is known as a transmission spectrum. Okay? So you will note that where there is this bump in the absorption is where, in this particular case, there is water vapor in the planet's atmosphere that is absorbing the starlight. Also important to note is the size of that bump. You see that is a few hundred parts per million. So a few parts in 10,000 is the kind of signal that you're looking at. So very small signals, which means to be able to detect that signal, your error bar, your uncertainty on that observation has to be a few tenths of parts per million. Crazy, right? So these are the kinds of observations you need to be making those detections. That was already possible a decade ago with the Hubble Space Telescope. Now, once you make such a measurement, the next step is known as atmospheric retrieval. Again, I'm just introducing several concepts here which we'll revisit later. Atmospheric retrieval, all this is saying is that now I have a spectrum that we saw in the previous slide. I couple that with a parameter estimation scheme. So this is just showing a flowchart. So you have your data, you have a parametric atmospheric model, which means a model that lets you explore a wide range of compositions in trying to explain that data. Okay? So when you do that, and there are various, for those of you who do this data analysis and stuff like that, so you're basically fitting the model to the data, and what you can get out of it are the composition, the chemical abundances in the atmosphere of the planet. Okay, so that's all there is to atmospheric retrieval. You have a data set, you have an atmospheric model, you explore the parameter space of the atmospheric model, then you can find the range of compositions, range of chemical abundances that will match your data. So when we are saying we detect a certain molecule, that's what we are talking about. We find that region in chemical space where some composition will explain the observation that you're seeing. Okay, so this is atmospheric retrieval. So this is the part where I had been fortunate to be one of the people who have introduced atmospheric retrieval to the field. That was already more than 15 years ago. So this is a very well-developed area, atmospheric retrieval. So now if we put all of this together, what are the big breakthroughs happening now? Why are we having this talk now, not 10 years ago? That's because of the largest telescope humanity has ever built in space, that is the James Webb Space Telescope. I'm sure you have all heard about JWST. This is a phenomenal game changer in understanding planetary atmospheres for two reasons. One is just the sensitivity of the instrument. So you can see the kind of error bars we have here. These are getting you down to few tenths of parts per million, but over a wide range of wavelengths. So the previous spectrum I showed you with the Hubble Space Telescope only went until 1.8 micron at the maximum for most observations. Whereas with James Webb Space Telescope, we now have almost the full near and mid-infrared wavelength coverage from 1 to almost 20 micron. So over that range, we are now able to detect molecules that we have never been able to detect before. Okay? So with HST, the only molecule we had been able to detect robustly was water vapor. That too for giant planets, mostly. Whereas with JWST, with one single observation, now these were literally the first observations with JWST like a few years ago, and you can see already this huge carbon dioxide peak. Okay? So just with one observation, we had detected more molecules than the entirety of Hubble Space Telescope observations of the decade prior. So that's the power we are talking about. So more sensitivity to more molecules, and also the sensitivity per molecule at any given wavelength range, you are going down to much, much more precise observations than was ever possible. So now this has ushered in a huge, dare I say, a revolution in our understanding of planetary atmospheres, and I won't be able to do justice to that whole field. I will just focus on our point here about the search for life. Okay? So now we have this phenomenal instrument, and then, as I mentioned to you, we have this set of planets, these sub-Neptunes. Let's put those two together and see if we can make any progress in the search for life. You ready? Let's do it. So that's going to be the outline of my talk. I've introduced all the important concepts to you, so you'd be able to relate to what I'm going to talk about. So I'm going to give you, in true fashion of any field at the very cutting edge, I'm going to show you some theory, I'm going to show you some observations, and I'm going to share some debate that's happening at the cutting edge. You ready for that? Okay, let's do it. So let's go with the observations. When we're talking about exoplanet habitability, I don't want us to assume that you just know that a planet will be habitable if it's at the right distance from the star. That is not the case. So when we talk about factors affecting planetary habitability, any given planet, there is a wide range of factors that usually affect whether the planet is habitable or not. Even the Earth has gone through various a turbulent past in our geological history, right? So just because the planet is at the right distance from the star doesn't guarantee that it is habitable. So I just wanted to show this slide up front saying there are a wide range of factors. But you got to start somewhere. Right? So the nominal working definition when people look for habitable planets, this is just a cartoon. Don't take this too seriously. This was from a long time ago, but serves to illustrate the concept of a habitable zone, which is if you put an Earth-like planet around a certain star, how far from the star do you need to be to have just the right temperatures that allow for liquid water on the surface? If you assume an Earth-like atmosphere and so on. So this is a good guideline. This gives us targets to work with, right? So once you have a planet, you know its mass, you know its radius, you know its distance from the star, you have a first check as to is it even reasonable to assume that this can have liquid water on the surface. So that's all it is. The only important thing I want you to note is that as the stars get smaller, these are called late-type stars. You go from sun-like stars all the way to M dwarfs, which can be a tenth of the stellar size. The star gets cooler, which means your habitable zone now can be closer to the star, right? You can be closer to the star to have the same temperatures. Now, if you take that sort of a concept, and let's say, let's ask this question, how many planets do we know of that are potentially habitable, Earth-like habitable planets around any kind of star? So this is a plot showing temperature, equilibrium, some average temperature versus planet radius, and also showing here period and so on. So let me put a small box around Earth-like properties, Earth size and Earth temperature, roughly 300 Kelvin. That's your box. I'm not doing a good job at keeping your hopes up, am I? That's all you've got. We have just a handful of planets. Admittedly, there are some more newer planets discovered, and we keep discovering newer and newer planets. But we are only talking about a few planets around nearby stars. If we are literally focused on Earth-like planets, Earth-size planets, Earth temperature planets, there are only like a handful, maybe 5 max, right? So this is what prompted us to reconsider this question. Now, if I focus on just Earth-like planets in the search for life, it's not good news, right? So the natural question for me to ask is an empirical question, which is, well, is it real? Do we really need to focus on these sorts of planets? Can we expand our horizons a little bit? Can we ask the opposite question of, what are the limits on planet mass, radius, temperature, all the bulk properties that do allow for habitability? As simple as that question sounds, it's actually quite a profound question, because deeply embedded in our psyche is this desire to find life on an Earth-like planet. That's not too far from the geocentrism that we had 500 years ago. We are wired to think like that. So actually asking this question itself is quite a profound exercise. So that is what led us to this new paradigm in the search for life. That's the Hycean paradigm. Now, let me give you a brief history of how this came about. This is the subneptune K218b. This is a planet that's about 9 Earth masses in mass and about 2.5 Earth radii. And the main thing that's going good for this planet is that it is in the habitable zone of its host star. Means the irradiation it receives from its star, which is a small star, an M-dwarf star, is close to what the Earth receives from the sun. So if you had an Earth-like planet at that distance, this would be a really good target for our geocentric view. But it's not. It's a bit too big. So if you asked 5 years ago, anyone, would such a planet actually be habitable? The answer would be a unanimous no, me included. Right? Because our concept at that time is that such planets are just too large to be habitable. You expect them to have deep envelopes like Neptune and Uranus in the solar system, and the pressure and temperature at the bottom of that would be too high to allow life. Okay? But turns out I was also in that same camp, and turns out I was very wrong. So these were some Hubble observations obtained at that time with a lot of HST time. This is over 50 hours of Hubble Space Telescope time, which is a lot of time. And these several groups had obtained 2 data sets two instances of the data from the same observations for this planet, and we used one of those data sets from this study. And what we found was that, so all these studies together agreed that there was a blip in the spectral feature. Do you remember from our spectroscopy course that we did 20 minutes ago? In a transmission spectrum, you saw an absorption peak for water vapor, right? So that is that peak for K218b as well. Okay, so that little peak. But that was not good enough because there was a debate around the time whether that was really due to water, because water and methane have very similar features in that band. So there was a lot of debate going on. What we did, nevertheless, was went ahead and said, let's build internal structure models of this planet and see the full range of possibilities for what an interior of such a planet could be, if I take the bulk density, right? So this is a slightly complicated plot, so bear with me. All it is showing the mass and radius, and these are showing curves of uniform composition. So if you take an iron ball, an iron sphere, and if you change the mass, what would its radius be? How would its radius change? That's all that's showing, right? The variation of radius for mass for uniform planets. So that's for an iron sphere. That is for silicate, and the blue is for a pure water planet. Okay? And what you'll see is that generally a lot of these points lie in between those curves, which means different combinations of this material can explain the mass and radius, the density. Except for K218b, it's sat just above the pure water curve, right? Which means you need a hydrogen-rich envelope, an even lighter molecule to explain the low density. And because we saw a hydrogen-rich atmosphere in the planet, that helped. But then the question is, well, you have a hydrogen-rich atmosphere, but what can the interior be like? What are all the possibilities? So we came up with 3 combinations that are possible for this planet, and those are these 3. One is the planet can be a rocky planet with a large hydrogen envelope that can explain the density. It can be a Neptune, a miniature version of Neptune with some rocks, some ice in the loose sense, high pressure volatiles, and then a hydrogen-rich envelope. But then there was a third kind that had not been considered before. That is where you have a lot of water and a very thin hydrogen-rich atmosphere. Turns out, and we were just doing this as a generic exercise, just exploring the space, but turns out, if I plot, these are internal structure models coupled with an atmospheric structure model, and if you just plot the temperature and pressure at the boundary between the atmosphere and interior, and see where does that lie on the water phase diagram, this is the plot you get. Okay? So those are the red curves, the loci of the boundary. HHB is the boundary between the hydrogen-helium atmosphere and the water layer. And you see that for most of those cases, the planet is just too hot. the surface is just too hot to even have liquid water. However, there was a small range of solutions, very small segment of these solutions, which did allow for liquid water. Okay? So yes, in most cases, the planet would not be habitable, but there was also a non-negligible chance that you could have a liquid water surface on the planet. And this is another example of an atmospheric structure model and showing how you can have different properties of the atmosphere and allow for a liquid water surface. Now, this is great because we went, this is all standard modeling in the field, but the implications are profound. We went from saying this planet cannot be habitable at all, not only this, no such planet can ever be habitable, to saying that there is actually a non-negligible chance that this planet might be habitable. Now, I was trained as a theoretical astrophysicist, and whenever you see strange phenomena, it's a cause for celebration. Because there is, in my mind, I always have this principle of infinities, which is, because the universe is so infinite, you just have to come up with a crazy idea. It's got to be there somewhere. You see, so this was great, right? So what we said very quickly after that, hang on a minute. If K218 has a small chance that it could be habitable, let's just explore the entire space of possibilities and see which other planets can have similar conditions theoretically. And that is where this concept of the Hycean worlds was born. Okay? So we just saw from K218 you have a hydrogen-rich atmosphere and an ocean-covered surface that is possible. So we combined them, and the word Hycean stands for a hydrogen-rich atmosphere on an ocean-covered surface. It's a portmanteau of hydrogen and ocean. So we found that when we explore the full space of possibilities, there are actually several other planets that also fall in this range. So that cyan region is the region where such planets can exist, the mass and radius of planets in that range with temperatures below about 300, 400 Kelvin, around that range, depending on the star, of course, can all fall in this category of Hycean worlds. And that's how this concept was born. Purely theoretical from one observation 5 years ago. Okay? So we went ahead and now said, well, we talked about the classical habitable zone for Earth-like planets. What would happen for Hycean planets? And the habitable zone just expands enormously. It's huge. That entire cyan region is the region where you can have a planet that is significantly larger than Earth, up to 2.5 times Earth size and up to 10 times Earth mass, roughly, and a wide range of orbital separations, and it could be habitable. Isn't that cool? See, this is why you do theory. In theoretical astrophysics, you get to play with concepts and come up with new objects, and then you can test it in the cosmos. And that's what I'm walking you through today. Now, I've given you how it came about theory, but then I gave this as an exercise in my class to come up with a new planet type. So some basic design basics is that if you saw the transit depth is this ratio of the radii squared, but then the atmospheric height is related to the temperature. So I asked my students to come up with a planet that can be habitable and has the best chance for detectability. Right? So then you have to optimize basically the size of the planet. The larger the planet, the more observable it will be. Right? The atmosphere being hydrogen-rich means it's lighter, so it's puffier. Right? The star, if the star is smaller, your transit depth is also higher. So you put all these things together, and inevitably you'll come up with a unique solution that is a Hycean world. Isn't that cool? Yes. So my students came up with it, and I was quite proud. So that's it. So in red, oops, what did I do? Sorry. Okay, we're back. Press the wrong button. So in retrospect, this was always there to be discovered theoretically. We just came about through a planet, but if you go back to your drawing board, you'll easily discover Hycean planets theoretically. So that's what we have here. These are planets that have hydrogen-rich interiors and surfaces, water-rich interiors and ocean-covered surfaces with hydrogen-rich atmospheres. Now we have identified about a dozen such planets that are out there around nearby M dwarfs that we can observe with the James Webb Space Telescope. And this was a prediction before JWST was launched. Again, in astrophysics, it's quite a prized possession if you can make a theoretical prediction that is testable, right? So then you go ahead and test it, and then you can verify and so on. But how do we confirm a Hycean candidate? I've just told you that such objects exist, but how would you know when you look at a planet, how would you know that it definitely has an ocean? So there were several teams that followed up on our work and did chemical calculations. What they did is, this is actually quite an important development in the field. There were several of the studies that came in the same year, right after our work, and we also followed up in another study. So the concept is that if you have a deep atmosphere, a deep hydrogen-rich atmosphere, let's say like Neptune, what happens is that a lot of the primary molecules like methane, water vapor, carbon monoxide, carbon dioxide, all these molecules tend to be, or ammonia, another molecule, tend to be in thermochemical equilibrium. Okay? Which means that if you put a certain number of atoms in a box of a certain temperature and pressure, you can predict how they partition into different molecules. That's thermochemical equilibrium for you. Okay? So deep atmospheres, when in the deeper parts of the atmosphere where the pressure and temperatures are high, thermochemical equilibrium is maintained rigorously. So even if in the upper part of your atmosphere that can be disturbed by various process, photochemical process, in other words, interaction with the radiation, cycling, and so on, those molecules can always be recycled from the bottom of the atmosphere. So you expect to see molecules like methane and ammonia in those atmospheres, as we do in the solar system giant planets. But if you have a surface and only a shallow hydrogen-rich atmosphere, what it does is it cuts off that recycling. So you can no longer recycle these top molecules like methane and ammonia from the bottom. Okay? So you should see a depletion, especially ammonia, which is very soluble in water. There is a prediction that you shouldn't see ammonia if it's a Hycean world. You should see ammonia. You should not see ammonia if it's a Hycean world, but you should see ammonia if it's a deeper atmosphere like a mini Neptune. Cool prediction, right? So there were other predictions like that. The ratio of carbon dioxide to carbon monoxide is another prediction. If you see more carbon monoxide than carbon dioxide, that is another prediction for a deep atmosphere. So all of these predictions had been made, again, before the JWST observations were taken. So these are all predictions. So I think you are now well equipped with all the theory that is needed to go make our observations. Okay, let's do it. So before we make our observations, our talk here is about search for life, right? So let me give you just one slide about what is it in terms of a biosignature are we looking for, and how detectable is it with JWST. So we are entering the observability part now. So again, we started thinking about Earth-like planets. Now, if you have an Earth-like planet in the literature for decades, the biomarkers people had been thinking about are the common ones. You have oxygen, you have ozone that's coming from oxygen, you have methane is a good biomarker, although not exclusively so. There is a small amount of methane that can also be produced geochemically, but for the most part, it is a biological molecule. There's another molecule, nitrous oxide, which is a very good biomarker. What do I mean by a biomarker or a biosignature? These are molecules that are uniquely produced by life. Okay, and don't have significant false positives, as in other words, other non-biological processes that can make them. So those were the top biomarkers for Earth-like planet. But over the last more than a decade, several studies had concluded that actually, if you have a hydrogen-rich environment, those may not be the best biomarkers. Okay, there could be other molecules which are also produced by life on Earth in small quantities, that may be more observable and better biomarkers if you have a different atmosphere, like a hydrogen-rich atmosphere. And the same was predicted. We predicted that for Hycean worlds as well. So what are those secondary biomarkers? So I'm showing you just here a list of such molecules, and one of them is dimethyl sulfide. Name rings a bell? It will soon. So dimethyl sulfide and a few other molecules, methyl chloride, and there are these molecules which are produced on Earth by life in very small quantities. We are talking about part per billion quantities. But in other planets, hydrogen-rich environments, and where you have large oceans, they could be produced in higher quantities. And as you have seen, because of the hydrogen-rich atmosphere and larger planets, they're more detectable as well. Okay, so those are the kinds of planets we'll go, kinds of molecules we'll go looking for when we're talking about biosignatures. Again, this is just a slide to show you the kind of spectral features we're expecting. These are showing the molecular absorption cross-sections of these molecules, and you'll see that most of them have features, strong features in the infrared. And that should ring a bell because that is what JWST is good for. Right? JWST is a predominantly infrared telescope with extremely high sensitivity. So it's the best match for looking these kinds of molecules. So we already showed this slide just to see like how good JWST is. Now you can do some calculations on how detectable are Earth-sized planets. Now this is showing an example for a planet system called TRAPPIST-1. Some of you may have heard of this. There are 4 habitable planets in this system, and the star is very small, about a tenth of this solar size, the size of the sun, which means it's about the best Earth-like, best system with Earth-like planets where we can detect these things. And even there, we need several tens of transits. We are talking about hundreds of hours of JWST time to be able to detect a molecule like oxygen or ozone. So a lot of time, right? So very difficult. And people have tried that with initial observations, and we're finding that it's actually even more challenging than we thought, because the star, if you're going to small stars, the star being small helps, but they're also extremely active. So those mess with the observations as well. So when we do these sort of simulations for Hycean planets, suddenly they become a lot more observable and a lot more detectable. And this, again, was done before JWST was launched, these calculations. And we showed that if you have a Hycean planet and if you have these kinds of molecules in the atmosphere, we should be able to detect them with a few transits. And we are now talking about tens of hours of JWST time. Okay? So that is what kickstarted this whole effort just 5 years ago, the prediction that there are habitable planets in which you can detect biosignatures with JWST with a reasonable amount of time. Okay? So then, with that, armed with that optimism, let's go into the observations. So we are talking about K218b. Now I'm going to show you the latest and greatest observations of a small habitable zone planet. So we got the introduction about K218b. We saw what the HST observation looked like, right? So just some, for those of you who are interested in observing and so on and so forth, we observed it with 3 different instruments on JWST, all the way from roughly 0.9, 0.8 micron, all the way till 12 micron. Those made of with 3 different instruments called NIRIS, NIRSPEC, and MIRI. All the information is on here. And you can see each observation is only order like 6-7 hours maximum, including everything. The observations shown here are purely the science observations, but you also have some observation overheads on top of it. But we're only talking about order 7 hours max for each observation. So you saw this observation, right, with the Hubble Space Telescope? You're ready to see what the JWST spectrum looks like? I'll wait a bit. No. That's what it looks like. Can you believe it? Only 14 hours of JWST time. Just 2 transits, 1 in each instrument. Look at all those peaks. There are 5 peaks in here of methane. So the feature that we thought was due to water vapor, turns out it is actually methane. But we know that robustly now. And then look, there is another feature here of carbon dioxide. Okay? We'll get into more detail on this, but I think at this stage it's important to just pause and reflect on this, because this is literally the first time carbon-bearing molecules have been detected in a planet outside the solar system in the habitable zone of its host star, ever. Right? We can argue, debate about the interpretation and all that, but the case remains. Right? This was our first encounter with a planet in the habitable zone, and we know that it's got carbon-based molecules robustly. Right? So this was super cool. And I'm just showing you this plot for reference, showing all these molecular features that you can see, and we are now seeing them in the spectrum. And now you will recognize this plot, right? Atmospheric retrieval. So we took that data and conducted atmospheric retrieval on it, and what you derive are these estimates of the various molecules. Okay? So these are methane, carbon dioxide, these are called posterior distributions. These are probability distributions of the abundances of these molecules, mixing ratios of each of these molecules. So basically, wherever you see a peak, you will recognize that that is getting close to a molecular detection. And where you have no peaks like this, that means you're not detecting this molecule at any significant evidence. And then you have molecules in between where you have somewhat of a peak but a long tail, which means it's a maybe. That is all the statistics you need to know. So here you can already see from this plot that methane and carbon dioxide are robustly detected. Several molecules like water vapor, ammonia, carbon monoxide, and this molecule Hycean are robustly not detected, right? And then there is this one molecule which is in between. And that is what I mean when I say we found a hint of DMS, which we saw in the previous slide, that is a potential biomarker, right? So this result kickstarted the whole new era of observational characterization of temperate sub-Neptunes, if we don't want to call it Hycean worlds, but small planets in general. And I've summarized all these results for you, and you'll recognize that these results, the non-detections of ammonia, CO, and H2O, and the detection of CH4 and CO2 are consistent with our previous predictions from chemistry. You remember that, right? When we said if you don't detect ammonia, that is indicative of a shallow atmosphere. So the picture hangs together that whatever we said is a prediction for a Hycean world was matched by observation. It is so hard to believe, if you think about it, right? We come up with an abstract theory completely out of the blue, and we said, maybe there are these planets in the universe, and then you make an observation, and what are the odds that your observation sits right on top of your predictions? We could have gotten lucky, okay? So we, in the paper, we said, now just what I just said, that these match the predictions for a Hycean world. So it's a possible Hycean world. We don't want to be so definitive. We want more observations and so on. But that launched like a new era of atmospheric characterization of these small planets. And if we pursue forward, maybe we'll get lucky and also find a robust evidence for a biomarker. So this hint of DMS that I mentioned to you before, now we said let's go and look for an independent line of evidence to see if there is further evidence, any hint of DMS. Rational thing to do, right? So fortunately, we had a different, the third observation, which I didn't show you earlier, which was in the mid-infrared, was in this range, between 5 to 12 micron range. It's called the MIRI instrument, the mid-infrared instrument. And if you plot what are the predictions for DMS and DMDS, this is another molecule, also a biomolecule like DMS, you see all these spectral features. Those are theoretical predictions. And now, let's see what the observations look like. You ready? It's tantalizing, isn't it? It's just too good to be true. There we go. This was an observation done blindly with two different data reduction methods. We think the spectrum itself is robust. but we see the peaks of DMS right on top. Right? So again, we go back, we do these retrievals we talked about, and we saw peaks for DMS and DMDS. Now, why did I bring DMDS into this story? It's because we didn't want to be complacent and look for just DMS. You see, if we just looked for the molecules that we looked before, and we saw that spectrum just now, and it looks like DMS, we could stop there and say it's DMS. But we should be a bit more robust than that. So what we did is we searched 20 molecules to see if we can find any other molecule that can mimic those features. So at that time, 20 molecules was the largest number of molecules ever searched in like one of these like sub-Neptune exoplanets ever in the field. So we did a thorough search, and we found that this other molecule, DMDS, dimethyl disulfide, as the name suggests, is a close family member of DMS, also has similar spectral features. So we said, let's also throw that into the mix. And we found that either molecule could explain the data. So you need one or the other molecule or both. So that's what these peaks are telling you. So that to us was yet another big breakthrough. Now, in all of this, it's easy to take these things for granted, and I'm not saying these things explicitly, but now I will. As exciting as this confirmation is, also this is still tentative, I should say. We need more observations. This is the first spectrum in the mid-infrared of a habitable zone planet ever. So in passing, in all of this narrative, what is lost is that we are making huge strides, first time for humanity kind of strides, with each observation. So we can argue all about the interpretations and all of that, but I think as a society, as a civilization, we should just take a step back and marvel at our capability as a civilization that we're able to make these observations and have a fighting chance at detecting life. Right? So to us, it's all mind-boggling when we are working on these sorts of things. So these are two independent lines of evidence. First we saw in the near-infrared, then we saw in the mid-infrared, and the detection significances are both marginal. We are talking about 2-3 sigma level detection significances. What does that mean? That means order 95% confidence levels, 99.7% confidence levels, and so on. And there are a lot of debates going on in how to interpret these statistics in the field right now. So we can just have upper limits on these detection significances. But the point remains that these are credible hints that we want to follow up on. Right? But even to be here is a big deal. So now let me enter into my very last part of the talk. So I've given you the landscape of theory, how we went from being hopeless at the beginning of the talk to trusting a theorist to say that there is hope, and coming up with a class of planets, an imaginary class of planets that we could look for. Then I showed you observations, which are breakthrough observations made possible by the best of our facilities that are available now. And we are seeing this congruence between theory and observations, which is amazing in astrophysics. That's the entire history of astrophysics is the history of amazing coincidences like that. Okay? And this is one of them, and I'm very proud of that. But now let's get back to the nitty-gritty of things. So we are seeing tentative signs. Now, is this real? So we want to ask all these questions. Okay? First, is the signal that we are seeing authentic? Is the signal adequately identified? Is it DMS that we are seeing, or is it some other molecule? Are there other sources that are non-biological that can also explain DMS? Would life produce such a signal given the environment, a Hycean environment, right? And are there independent lines of evidence? So when we write these papers, when you do observations for the first time, you always have a huge burden on your shoulders because you don't know if you've made an error somewhere. That's literally the first time someone is making that observation. You're literally doing the data reduction for the first time. You don't know, right? You just put your best effort. So we try to answer all these questions a priori when we write the papers, when we make the detections. But what is also important is that after the fact, we remain very keen and open to see what everyone else does with the same data ultimately science is a community exercise. We have to reach to some sort of a consensus at the end of the day. So as in that spirit, we have been pursuing more, trying to answer all these questions. But there have also been several others, teams around the world that have been trying to answer these questions. So in the remaining few minutes, I'll just take you to that to the forefront of that debate on what sort of arguments are happening back and forth. So you get like the true spirit of what's happening at the cutting edge of science. One of the very basic things to ask is the signal authentic? So if you do like a very crude exercise of just drawing a flat line across all the points, then one could argue that your flat line can go through several of these points. What that flat line test does not consider is the structure of the points with respect to the wavelength. Right? So if you did this flat line test, and if all the deviant points are distributed randomly across that flat line, so there's a good case to be made that there is no signal there. But with your eye, do you feel that spectrum, if I didn't have the flat line, that it's random? It's got some structure. And I even showed you a theoretical model up front before the observations were taken, right? So you want to use some credible models to see if you can explain the data. So in this work, what they had also done is used a double Gaussian model, one a Gaussian and another inverted Gaussian. There is no physical model in the universe that behaves like that, but let's take it as a toy model. And what they found is that when you do that, even if you took a toy model just trying to match the bumps and the valleys and so on, you get like a 2 sigma significance preference for that model than a flat line. Okay? So that is giving you the clue that there's got to be some structure there, even if at 2 sigma level. 2 sigma means 95% confidence. So that's the takeaway, is that even an unphysical model, like a double Gaussian, is still preferred. So it is not surprising then that if you use real models, you'll get a slightly better fit to the data, right? Common sense. There are other efforts that happened in the field, other teams going ahead and doing the same sort of the analysis by combining the data. So you can combine the high signal to noise and high resolution near infrared data with the low resolution, low signal to noise mid infrared data. What effect that has is to completely ignore the mid infrared data for the most part, because the error bars are too large compared to all the other data that you have in the near infrared. So your fits, your preferences are more biased towards what the near infrared spectra find. And even with that exercise, there are instances where you can find up to 2.8 sigma. Okay, so there is still hints. Now, each of us interpret these things differently. If you tell me that you found a signal at 2 or 3 sigma, I would say it is a good signal for following up. But you could also turn it around and say that it's not sufficient enough to call it detection. Right? So all of these are different narratives. So when you see in the field that someone saying that, oh, it's not, the signal is not sufficient, that is what they mean, is that it's not sufficient to call it a detection, but it could be sufficient for follow-up, to be interesting enough. Now, why am I saying all of these things? It's to set the boundaries for when do we call a detection of a biosignature. It is not at the level where we are right now. We have these inferences at a 2 to 3 sigma level. We want to collect more data and go up to 4 or 5 sigma level, at which point we'll confidently claim that we have detected it. But until then, whenever you hear stories in the news saying hints of life or hints of biosignatures, this and that, this is what we're talking about. We are finding signals at a 2 or 3 sigma level. We have a lot more work to do, but it is interesting enough to say that we are on the path. Okay? Now, this is not unique to K218b, of course. I want to say that because it is very important to establish uniform standards in the field. This is just a press release, came just a year before our results in 2023 with our previous first result. And you can see that here clouds were detected or claimed detections of clouds at 2.6 sigma. Okay? So this is a narrative that's used in the field commonly, and you can see that the feature here is also coming from just those few points. Okay? This is all what is done normally in the field. There is nothing specific to K218b. Same for another for another planet, these are the significances that are quoted, 1.93 sigma, which are quoted as results worth following up. This is another example. And I show this because this is a good quality spectrum, as you can see, of the same similar quality to what I showed you for K218b, but this is for a giant exoplanet, like a Jupiter-sized exoplanet. And here, also, the sulfur dioxide was claimed at just about 3 sigma. So similar to what we have for DMS. So across the board, this is to answer the broad question of the debate, is that are we doing anything special to our data on K218b to make these inferences possible? The answer is no, actually. There are exactly similar, very similar, with the same exact instrument, very similar observations obtained for other planets, also inferences made at the same level of significance. Some call them detection, some call as inferences, and these are community-wide efforts. You can see the number of authors. There must be 50, 70 authors here, right? So this is the state of the field. So if we have to question any of these detections or inferences, we have to go back to the drawing board and refine our methods across the board. And that is important, because we want to have the same standards for a biosignature as for any other molecular detection, right? And that is when you can ensure that science is as robust as possible. So that is number one. Is the signal, the second question is the signal uniquely identified? Let's say you do have a signal. How do you know for sure that that is from DMS, right? So far, we have tried our best at that point until April this year. We tried 20 molecules, and we could find only 2 molecules that explained the data. Soon after, another team went ahead and went much beyond. They said, why stick with 20? Let's look at all the hydrocarbons for which we have cross-section data, regardless of whether they're possible or not in this planet. Let's not worry about the physical plausibility for a minute. Let's just do a blind search of 90 molecules. And sure enough, they found 8 molecules that come to about 2.5 sigma significance, comparable levels to where we are. That's great, right? So what they've just done with this one exercise, which I think is a very good development in the field, they have expanded the volume, the search volume for molecules, right? We stayed with 20, and we were patting our backs, saying that was the greatest number of molecules that have ever been searched. Within a few weeks, less than a month actually, of our work, they went ahead and searched for 90 and found 8 molecules. We said, actually, that is great. So we are very keen observers of the debate in the field, and if there's a good idea, we'll take it right on. So we said, let's go. Why stop at 90? Let's take every single molecule for which there is cross-section data out there and search. And guess how many we looked at? 650 molecules. In just about few months of our supposed breakthrough with 20 molecule search, we went by an order of magnitude higher, 650 molecules. And what we found is that indeed, we found 14 molecules that could come close to explaining the data at the same level as DMS. Okay? One little glitch is that most of these molecules are not naturally produced. Many of these molecules are produced by life, and some of these molecules are anthropogenic. Okay, so we don't want to go that far. In case you're imagining anything, don't. This is an exercise of robustness, right? So what we did, we went one step further. This was all exercise just for the MIRI data, but we said we also have near-infrared data. Let's look at those as well, and we did. So this is a big effort from my team. Several of my members are sitting right here. We took those 14 molecules and also looked in the near-infrared data to see if there is any further evidence. And we could find only a couple of molecules which have any peaks whatsoever. Remember when I showed you this 14-hour observation, I said there's a tentative hint of DMS? We could find only 3 molecules with that, and DMS stands out amongst all of them. Okay? So the story where it ends right now is with this sort of exercise, we looked at hundreds of molecules, every single molecule that's out there, and DMS comes out as our best bet in terms of explaining the data across the mid-infrared and near-infrared. Of course, we keep going in terms of robustness. There is another team that came and said, question like the actual data reduction. So you can see, so these data, they showed our data, and then they could reproduce our data. And they said that if you change, I'm getting too much into the technical details here, but how you bin the data can change your spectrum a little bit, and that can influence your signal, DMS signal as well. And that is the plot that is shown here. Again, results from retrievals, which you're all experts on by now. So you can see that in all these cases, there are only a couple of cases where there were peaks seen for DMS, but in many of the cases, there were peaks for another molecule. This is chloroethane. So that was used as an argument that maybe the signal for DMS is not real. Except, I've already given you the answer 2 slides ago, which is when we did our own search, we also found in those 14 molecules that chloroethane actually sits at the top if you did that exploration. So sure, you could do all kinds of data reduction, and our expectation is that you should find one of those molecules that we are finding in our big search, right? And our claim is that any molecule we find so far is not across the board, from mid-infrared and near-infrared. We haven't been able to find a molecule that is purely abiotic. So either the instrument is behaving in a way that we don't understand, and whatever features we are seeing are systematics, right? Some instrumental effects that are masquerading as features, or we're seeing some molecule that we don't understand, and it could be potentially from biosignature, from life. Either way, it is very interesting. In terms of systematics, I just want to leave you with this slide, just compiling everything, just to emphasize the point that in terms of the methodology of how we are going about detecting, we are very, very careful to ensure that there is literally no change from what others have done on other planets. And that is very important to establish uniform standards. And this is just one snapshot of all the results, of the 3 results I showed you, the DMS case, but also these 2 hot Jupiters, which have exactly the same number of molecules explored. You can see that in this case, there were only 2 molecules explored to detect SO2. In this case, there are 4 molecules. In our final case, after selecting from 20, we also have 3 to 4 molecules included. They're all of the similar nature. Okay, so the point I want to take away tonight is that whatever in terms of methodologies, instruments, techniques, retrieval techniques we are using are all standardized. So anything that is popping up that is different from other planets has to be a source that is not based on the techniques that we are using. It's based on either the planet or an instrumental systematic that applies to all the data sets. Okay? So this is science at the nitty-gritty that you're seeing. You don't just claim a molecule. You have to do the due diligence to understand every step of the process and ensure that it's all uniform across the board. So now, at the end of the day, you ask me, so how confident are you? Right? Is there DMS on K218b? And I present to you my answer. Remember when I started by saying it took us 500 years of history to get here from first establishing the sun as the center of the solar system. Historically, when you read things, you read in terms of years, decades, centuries, and it all looks very romantic. But when it comes to actual science, we expect results to happen immediately. Right? The observations, these were just the first observations that happened this year. Right? It'll take us some time. We need the patience and the due diligence to get to the bottom of all of these things. Right? So in one sense, you can take away saying, we are not sure of DMS, whether DMS is there or not. We shouldn't pursue. That's the glass half empty view. The glass half full view is that we have enough evidence to keep looking because the path to a 4 or 5 sigma result is through the 2 and 3 sigma results. Right? Your signal isn't going to pop on the first observation. You're going to accumulate signal. And every 5 sigma result, unless it's like methane or something, but we're talking about biosignatures here, really faint molecules. So when you talk about those molecules, every 4 or 5 sigma result has to go through the 2 and 3 sigma results. And that is the glass half full view, is that there is optimism, which I promised you at the beginning of my talk, to keep going. There is one other minor reason for my optimism, if I may indulge myself here, which is more data is on the way. And just this summer, another team obtained, and they were kind enough to involve us in that exercise, to obtain more near-infrared observations of exactly the same kind that we had observed before. And this is, again, complicated plot, but you're all now experts on retrieval. So you can read the histograms, but you can see the DMS signal pop up again. So what they've done is they've added several more observations in different wavelength bands, but at least 2 more observations in the exact same NIRSpec band where we were claiming DMS in these regions. And with that, if you take the exact same retrieval setup that we had before and apply it to this cumulative data now, the significance increased. So the thing where I said very tiny evidence, maybe 1 sigma, maybe not, now within the near infrared, it's already about 2 sigma with the same retrieval setup. Okay? So that is another reason for my optimism, is that if we keep putting more and more time on it, and if the molecule is there, it will show up. Okay? You happy? Cool. Let's end with the final outlook here. So these are the inferences for K218b. We've detected carbon-bearing molecules, which is already a huge breakthrough, and the non-detections of ammonia and carbon monoxide indicate a water-rich interior. I've given you all the details about DMS and so on. There is a lot of debate going on, but there is a lot of hope also that if we keep piling more and more observations, that the truth may be clearer. There is enormous congruence of theory and observation, irrespective of the DMS and the biosignature, congruence of theory, a theoretical prediction and the observation, which is a key, a major achievement in astrophysics in general. Various open questions I'll leave you with. Is a liquid ocean surface possible? I only talked about the debate around DMS, but obviously there's a lot of debate on other aspects also. How do you infer the ocean? Is a liquid ocean surface possible? Is a deep H2-rich atmosphere possible with no ammonia? What are robust indicators of life? How common are these planets? All of these questions are being heavily debated in the field. I'll just leave you with some other teasers. If you ask, is K218b unique? Did we just get lucky on one planet? The answer, as you obviously know now, is no. So this is another planet called TOI 270d, for which we also have similar observations, and it's also showing similar kinds of composition. So this also, for 270d, we also have methane detected, carbon dioxide detected, and one other molecule, carbon disulfide, detected. If you were paying attention in one of my biosignature slides, CS2 is also a biosignature on Earth. Of course, we can't claim that it will be on this planet as well. We still have to do all the abiotic mechanisms explorations, but suffice it to say that we are seeing hints of molecules, excess absorption beyond standard on multiple planets at this point. This is all observational. On the theory side, we are also asking interesting questions. Let's say this planet is a habitable planet. What further theory can you do to understand what the internal structures, how deep the oceans would be like, and so on? And this is another recent work we did from my team. Again, several members of my team are sitting here, where you can easily calculate the depth of the ocean. It can be up to 1,000 kilometers deep. Okay? For reference, on Earth, the deepest part is order 10 kilometers or so. Okay? So these are fundamentally different planets, deep oceans, so deep that at the bottom of the ocean, you actually don't have a sea floor. There is no silicate sea floor. There is an ice bed at the bottom. So you go from ocean to high-pressure ice at the bottom. That's it. So then you have all the questions about, is life possible on such planets. Again, several of my team members are sitting here who work on these things all the time. We try to ask if those sorts of planets can have the right chemicals in the ocean to sustain this microbial life we are talking about. And the answer is, again, yes, there are mechanisms in which you can deliver bioessential nutrients to all these molecules. So a lot of theoretical work going on, a lot of observational work going on, exciting time in the field right now. At the very least, we started with this pessimistic view, and we are ending with the optimistic view that there is hope, right? So I'll leave you with these 3 fundamental advancements that have happened. We are probably, again, I won't be too definite, as you know by now, but we are probably seeing the first contact with potential habitability, let alone life. Forget life for now. But even the concept of whether a planet is habitable, we are probably seeing the first contact with that. And that's already a huge win for us as a species. And this planet, I haven't told you so far, is 124 light years away. Huge. That is, hundreds of trillions of miles, if you like. So that's one thing. Second bit is this congruence of theory and observation. That is a very prized position in astrophysics, as I mentioned many times. The ability to dream up and make observations, experiments to validate or to check those theories is the fundamental essence of science. So for all the young people, this is what one thing to take away is that the universe is so vast that you can always think of creative ways, using the laws of physics, of course, to come up with new objects and new experiments to test those new objects. And finally, we have landed on a new class of temperate subneptunes for which we are getting these data sets, and that could open an entire arena of planetary process, atmospheric process, internal structures, formation process, and so on. So the promise of this decade is that it serves as the launchpad in the search for life with the James Webb Space Telescope, but also large ground-based telescopes coming on board soon, and this vast range of planets, diverse planets that we have at our disposal to study. So we are really entering a new era in the search for life where there is hope to that pursuit right now as we speak. So where we started with putting the Earth in the center and asking, are Earth-like planets out there? Is there life on Earth-like planets? I'm sure you'll see this in a different light right now. So the new question we got to be asking ourselves is life a universal process? So it's not about finding little green people. It's not about finding aliens we can interact with. The notion is much, much more fundamental. We know the laws of physics apply universally at a cosmic scale. We know the laws of chemistry apply cosmically. We are entering a new era where we are beginning to address that fundamental question: is biology universal in nature? To me, that is a much more fundamental pursuit than just asking, are there aliens out there? You see what I mean? So in my mind, if you want to ask me the question, whether we will detect life, to me that is not even a question, because it's, of course, life should be there, because microbial life is very common, on Earth, and the process got to be very common in the universe. That is my belief. The bigger question I have in my mind, as you know by now, from a pure empiricist point of view, are we actually prepared to find life as we don't know it? In other words, if we see a signal of life, are we equipped to identify it as coming from life? So all the debate that's going on in the field are launching us onto that journey to answer this question. Thanks for your attention.